Hello, hello, and welcome back to Unconventional Computing CS492A in fall 2024 at KAIST. We're in chapter 2, creating our own optical computer. And as background, I've shown you a video about optical computing, conventional in a sense, optical computing, namely based on simulating Boolean gates, Boolean operations using light, using photons instead of classical electronic way. And I want to briefly recall a central section from that video, because at the end of chapter 2, I want to ask you how our own optical computer differs from this photonic computing. That was about what? Silicon photonics and about optical transistors in order to mimic classical Boolean gates. So this is, in a sense, still conventional computing. But what we're talking about now is optical computing in a different way. And at the end of this chapter, I want to end with a quiz that makes you think about the differences between silicon photonics and optical transistors on the one hand, and this new approach, unconventional approach to optical computing. To this end, let us recall what we have been talking about. We have been talking about mechanical oracles. So that's a recap. And to this end, we took an infinite problem, decision problem over natural numbers, and we've encoded that. That was our approach. And one way of encoding it is as a Zeno's comb, and comb with infinitely many tines, infinitely many teeth. Some teeth are absent, some are present. And of course, in order to have infinitely many teeth in a comb of finite length, the teeth must become smaller and smaller. That's why it's called Zeno's comb, because the tines become smaller and smaller. And in this way, we can fit infinitely many of them into a comb of finite length. This is like Zeno making infinitely many attempts in surpassing the tortoise, but each attempt becomes shorter and shorter, so that finally, within finite time, Zeno, Achille actually surpasses the tortoise. And then we discussed other ways of encoding such infinitely many Booleans, 0, 1, in the set or outside of the set, the decision problem, namely encoding them into a real number by using binary encoding. And this is the explicit expression in a sense, but it's not really explicit because this sum is an infinite sum, but you know from calculus that this sum converges. One of the essential properties of real numbers, it's a complete metric space. And now we want to discuss another way of encoding this uncomputable real number into a mechanical object, namely into such a rod. The essence now is that this rod has length, which is a real number, namely this real number. And then we can also use a similar trick, a similar method as with Zeno's comb. Namely, we can have a mechanical measurement of the length of this rod, approximately up to error 2 to the minus n, let's say. And this reveals the first n bits of this real number, and thus the first n entries of this decision problem. And by increasing the accuracy of the measurement, we can recover more and more bits of this real number in binary, and we can recover more and more entries and answers to these decision problems. And this shows that when we construct asymptotic computers, we might want to avoid such uncomputable real numbers that include encoding of the, for example, the halting problem, because if we allow such uncomputable real numbers, then we can simply use a mechanical computer that stores, that hosts such a rod of uncomputable length, like, for example, the standard of the meter in Paris, right? In Paris, there's this meter measure, which is the standard for all other measurements. And by the definition, this is 1 meter long. And so that's a computable real number, 1, right? And so imagine now a device that hosts such an uncomputable rod of uncomputable length. Then we can use that to solve many undecidable problems. So in the sequel of this lecture, we want to avoid this. We have deliberately considered this so far, but in the sequel, we deliberately want to only restrict to computable real numbers. And to this end, I reported to you without proof. Proof can be found in one of my other lectures, that every rational number is computable, has a decidable binary expansion, and the computable real numbers have nice closure properties. So, for example, if a real number is computable, then also the sign of that number, the cosine, and the arcus, tangent, hyperbolicus is also computable, which helps us when we now talk about optical computing. When we say angle is computable, that's the same as saying that the direction of the normal vector is also computable. That's the same. So in the sequel, we deliberately prohibit uncomputable coordinates and uncomputable angles and uncomputable directions. And we've already discussed some primitive optical devices, such as a plane mirror. Plane mirror is supposed to be perfect. So light ray that enters this mirror leaves this mirror at the same angle, so incoming angle compared and with respect to the normal is the same as the outgoing angle, a perfect mirror. We also talked about refraction. That means some transparent physical object, such as maybe some water or a block of glass. And here, when a light ray enters, it does not get reflected, but it enters the transparent material. However, it proceeds inside this material at a different angle, and the angle is determined by Snell's law according to the refraction index. So we have the refraction index of light of air, or maybe of the vacuum, and we have the refraction index of the optical material, which is usually larger. It's more dense, and this makes the light ray proceed in a different direction according to Snell's law. So these are two optical primitive gates that we're going to use in constructing an optical computer. And when we construct this optical computer, we suppose geometric optics. Geometric optics is an idealization. This is why this is part of the chapter on asymptotic computing, because the actual optical devices do not precisely satisfy these laws. but we suppose that they do so sufficiently well, approximately, and therefore asymptotically. This is going to be something we're going to use to construct an optical computer. So we suppose that the optical devices and the light rays we have suffer from no aberrations, no deviations from these ideal optical laws. So, for example, no chromatic aberration. Chromatic aberration means that the color of the light ray affects the behavior. Maybe different colors have different refraction laws, refraction index. Also, we suppose that the light rays do not suffer from defocus or from attenuation. So they're supposed to be perfect and infinitely thin, which in practice is not the case, but lasers, for example, are so intense and so thin that they're a good approximation. We suppose that there's no coma. Coma means imprecision of the optical objects. For example, some small deviations from a mirror being not perfectly planar, but maybe some rough surface. We suppose that light behaves in a geometric way, not like a wave with interference, nor like a particle carrying um, uh, impulse, carrying some force onto the mirror or onto the refractional objects. So these are our idealizations, and under these idealizations, every optical device can be also operated in the opposite direction. So when here a light ray enters and leaves at the same angle, we can do it in the other way. Reverting the direction of the light ray results in the reverted behavior. Same for refraction. If we have a light ray that leaves the optical device, the block of glass, then at an angle B, then it leaves the object at angle alpha, again satisfying Snell's laws. And this will be important when later we want to create an optical computer in order to simulate a Turing machine. That means we will need to have a so-called reversible Turing machine. But for now, let's proceed to another optical device, namely the so-called parabolic mirror. So this mirror here is a planar mirror, and now we want to consider a parabolic mirror. Okay, so what's the essence of a parabolic mirror? Well, the surface of a parabolic mirror is not planar, but it has the shape of a parabola. So here is a parabolic mirror, a mirror whose surface has the shape of a parabola. Now, parabola is one of the three conics. Conic means if you take a cone in 3D, and if you cut through it, then it depends on where you cut through it. And if you cut through it in one way, the result might be a circle, right? If you cut it horizontally. If you cut it in a U way, then the result might be an ellipsis, right? If you cut it in a different way, the result might be a parabola. And this is what we consider here. In the third case, hyperbolic, but here we focus on parabolic mirrors. And you may know from high school, perhaps, that parabolic mirrors have this nice property that parallel incoming light rays are all reflected onto the same point, the so-called focal point. Actually, there are two focal points, but we're focusing on this one here. It's a pun, focusing on this focal point. So wherever the light ray enters, only the direction matters, and all light rays coming in parallel all meet in this focal point. That's why it's called focal point. And now what we're going to do is we're going to cut away half of that parabolic mirror. Here, it's cut away, so that now the light rays kind of leave again, proceed from this focal point. But here we put in another inverted mirror, and then the light rays kind of proceed in the direction where they have been coming, but now with negated distance from the axis. So let's denote that a distance from the axis by x. That's the symmetry axis. And if a light ray enters here with this distance, then the reflected light ray also leaves with a negated distance. So this is basically how to negate data, real numbers, namely distances, using such a optical device. But our goal is not only to change the sign, but also to scale. Until this end, now we're going to modify this combination of two parabolic mirrors further. Then we were going to scale down the second departure parabolic mirror by a factor of 2. Still, there's a line to share the same focal point as the incoming parabolic mirror, but now the slope is half the slope of this parabola, still a parabola, but with a scale by a factor of 2. And then it's easy to see that the distance of incoming light rays, x, yields the distance of the outcoming light ray to the distance to the symmetry axis, which is x prime equal to x over 2. So that means this optical combined device of two parabolic mirrors essentially scales light ray distance by 1 over 2. And now remember that we have reversibility. So if we conversely have light rays coming in from here, then their distance to the symmetry axis gets multiplied by 2. Light rays coming from here, distance divided by 2. Light rays coming from here, distance multiplied by 2. And that will be a basic arithmetic operations in our optical computer, dividing by 2 and multiplying by 2, because, spoiler ahead, remember that multiplying by 2 of a number in binary corresponds to shifting left, and dividing by 2 of a number in binary corresponds to shifting right. So this will be our operation of left shift and right shift of real numbers in binary. Because now let's recall a Turing machine. The Turing machine consists of this halfway infinite tape. It starts here at the first position and then contains infinitely many cells, and each cell can store 1 bit, 0 or 1. And when we can encode the content of that tape as a real number in binary, right? Infinitely long binary expansion. So every possible tape content corresponds to one position here on this x-axis, starting with 0 and then moving further and further. And the largest real number we consider is 1. That's when all the tape cells have content 1, 0.1111. That's the binary, that's a real number 1. So it suffices to consider real numbers between 0 and 1 to encode infinitely many tape cells, the storage of a Turing machine. Now, what else do we need to recreate a Turing machine? We have this read and write head that can read the content of the current tape cell, 0 or 1, and then finite control, which proceeds according to the content of that cell and according to which state this control is in. It's like a finite automaton. There are finitely many states, and the state and the bit that is being read determines the next move of the Turing machine. The next move, the Turing machine can override, change the content of that tape cell, change 0 to 1 or 1 to 0, or keep 0 as 0, and then move the tape head one cell to the right or one to the left. The read-write head can move, and all this is determined by the state of the finite control and by the bit that it is currently reading. And then one move is over, and then it will make the next move. And then it will make the next move and the next move until finally maybe it ends, maybe it hits the left end of this tape, and then the computation stops, and the tape contains the result, the output. For decision problems, this could be 0 or 1 in the first tape cell, or it could be a prime number written here in binary, depending on what kind of computation the Turing machine is supposed to. And now we want to simulate this using our geometric optical computer. And we've already made a first step, namely discussed how to encode this infinite tape contents into one real number, namely into the distance of a light ray from the symmetry axis. So this is how we encode that. And actually, we want to encode also the position of the finite control. So what we're now going to do is we're only going to encode the part right of the finite control, and we're separately going to encode the tape contents left of the finite control into two separate real numbers. X is going to contain the part under the finite control and all the tape cells right of it, and possibly infinitely many, and the tape contents left of the current position, which are only finitely many bits, is encoded into another real number, y. But as the tape, the read-write head moves forward to the right, the part left of the read-write head can become longer and longer. So this is a finite part, but it can become arbitrarily long. So it's basically the same as the part right of the head, which is also finite but unbounded, and the part left is also finite but unbounded. So we simply suppose both to be infinite and to be encoded in two separate real numbers. So here's how we do that into an optical computer using now 3 dimensions. So far, the optical devices we have constructed operate in 2 dimensions, the mirror, planar mirror, and parabolic mirror. But now we extrude them kind of into 3-dimensional devices. And the light ray that enters our optical device comes through in parallel into such a square. And now we have 2 distances, the distance from the y-axis, that's the x-coordinate, and the distance from the x-coordinate, that's the y-coordinate, each one encoding the part of the tape of the Turing machine. So, and the light ray moves into z direction. So if the light ray enters, let's say, in z direction, parallel to z direction, at this point, then this point corresponds to a pair of real numbers, x, y, coordinates. And these coordinates together encode both the position of the read-write head and the content of the tape right of the head and left to the head as 2 real numbers. And let's say behind this screen, this is transparent screen, is now such a maybe parabolic combination of 2 parabolic mirrors. Then the light ray may proceed again in z direction, right? It comes in this is that direction, and it leaves in that direction, but with the x coordinate maybe divided by 2. And if we have a similar parabolic mirror for the y direction in reverse direction, then the y coordinate gets multiplied by 2, so that in combination, maybe the x coordinate becomes divided by 2. So this is half the length of this. And the y coordinate gets multiplied by 2. So this is twice this length of the incoming ray. So that this combination of two double parabolic double mirrors, one for dividing by 2 and one for multiplying by 2, can have this effect on a ray coming in that direction at coordinates x and y, and leaving at coordinate x prime equal x over 2, and at coordinate y prime equal y times 2. And what does that mean? If we multiply, if we divide x by 2 and if we multiply y by 2, that means that the right head has moved, right? So if we multiply y by 2, then that means shifting to the left. Shifting y to the left means that the right head has moved here. This is now closer to the right head. And if we divide x by 2, that also means that the right head has moved one cell to the left. So this gate, which is realized using two such pairs of parabolic mirror, corresponds to one move of the right head, one cell to the left. That's here, move to the left. And by having another device in opposite direction, we can also have an optical device that simulates a move to the right of the right head. So we're already making progress towards our optical computer. We can store and encode the content of the tape into pair of coordinates in the plane, and the light ray proceeding in the third direction, z direction. And we have a device that corresponds to a read-write head Turing machine moving one cell to the left, and another device that corresponds to a move to the right. Okay, by reversing it, reversibility, we obtain another device that corresponds to the head moving one cell to the right, namely multiplying x by 2 and dividing y by 2. So what else do we need in order to continue to create a simulation of a Turing machine? We need to be able to read the current cell content with 0 or 1, and then make a branch, in a sense, a test and branch depending on whether the current bit in the current cell is a 0 or 1. That is, depending on whether the x coordinate is larger than 1/2 or smaller than 1/2, right? Of course, larger than 1/2 means that the binary expansion starts with 0.1, and smaller than 1/2 means that the binary expansion starts with 0.0. So by testing whether the x coordinate is greater than 1/2 or smaller than 1/2, we can recover whether the content of the current tape cell is a 0 or 1, and then branch accordingly depending on what the finite control is programmed. So let's first discuss how to test that, and then we need to be able to write, maybe to flip a bit possibly, right? So if we don't change the bit, then there's nothing to be done in our optical computer. If the finite control says flip that bit, change the 0 to 1 or change the 1 to 2, 1 to 0, then we need an optical device that does that. So this is what we now want to discuss. First, about the test instruction, the branch instruction. As I said, this depends on whether the x-coordinate is greater than 1/2 or smaller than 1/2. Okay? And here's an optical device that does that. It consists of two planar mirrors at an angle of 45 degrees. Now observe that this angle of 45 degrees, that's a computable number, right? 45 degrees expressed in maybe in multiples of pi. That's a transcendental number, but it's a computable number. Or put differently, the normal of that skew mirror is in this direction, which is a computable normal. It goes in direction -1, -1, right? And similar, this mirror here goes in direction 1, 1. So we have two mirrors, and if the light ray enters at a x-coordinate, this is the z direction, z x-coordinate greater than 1/2, then it leaves at a x-coordinate x minus 1/2. So it's basically subtracting 1/2, which corresponds to flipping the bit. If this bit was a 1, then upon leaving x prime, this bit becomes 0. And in the opposite direction, this also corresponds to flipping a bit 0 into bit 1. So this is our device for writing, or more precisely for flipping a bit in the tape content encoded as x and y coordinate. In this case, we only need to change the x part, only flip this bit if it's necessary. So this is our flip operation in optics, flipping 1 to 0 or flipping 0 to 1, depending on which direction this optical device is operated in. So now we've already succeeded in flipping a bit. That's our bit flip operation. So instead of writing, we all have a flip operation. But we first test, we first read the current bit, and depending on what is to be written, we can then either flip it or keep it. So the next operation we want to simulate in our optical computer is the read operation of the Turing machine. And this is achieved with, again, two mirrors at a 45-degree angle, but now are arranged in this way, because here, if the input ray enters at an x-coordinate greater than 1/2, then the ray proceeds in this direction. If the input ray enters at a position less than 1/2, then it leaves in this direction. So depending on whether this bit is 0 or 1, the ray proceeds in two different directions. Now the x-coordinate gets lost, right? So the ray proceeds now, it enters in z-coordinate at a certain fixed x-coordinate. X is fixed and z changes. And now when the ray leaves, x-coordinate changes, but the z-coordinate is fixed, and the z-coordinate contains information about the input x, and also the direction contains information what is the content of that bit. And then we can place another optical device here and here, depending on what the final control said, what the Turing machine should do when reading a bit 0 and 1, respectively. So that's our read operation. And now we've prepared all the optical devices we need in order to combine them into one optical computer. Remember, the principle of computer science is taking few small primitive operations and combining them to obtain some very complicated behavior, such as, for example, using only bits 0 and 1, and using and or and not gate to build an entire PC, right? And similarly, now we have few basic gates, namely this parabolic mirrors and this subtract 1/2 two planar mirrors, and the test operation for this bit. And this, combining this will allow us to simulate an entire Turing machine by combining several of these three basic optical gates, if you like. And instead of bits, we here encode entire tape content, infinitely many bits, as a real number, namely the distance from the symmetry axis. And observe that we have not used any uncomputable coordinates or direction. These mirrors have 45-degree angle orientation, and the parabolic mirror have either slope 1 or slope 1/2 or slope 2, x squared times 2 or x squared divided by 2. Everything just simple numbers. And now, how do we combine these primitives? This is now depending on what the finite control of the Turing machine is programmed to do, the Turing machine that we want to simulate. In general, this would be a so-called universal Turing machine that can simulate any other. But the essential part is that this is a finite control, finitely many rules of the form. If the current state is Q, one of finitely many states, and if the bit you're reading here, then change that bit and move the tape head one cell to the right or one cell to the left. And this is what we're now going to do for one rule, and then for the next rule in the finite control. And there are finitely many rules. And for each of these rules, we're going to combine 2 or 3 of these basic optical gates. So this is our first optical gate. This is the test gate. So suppose that the finite control says if you're in state Q, and if this bit is zero, if this bit is 0, then move one cell to right, move one cell to the left. Our optical computer will then have such a test gate. It is labeled with Q, the state that we're currently simulating. It will test whether the incoming ray comes at an x position smaller than 1/2 or greater than 1/2, corresponding to this line in the middle. And if the rule says in state Q, when reading 0, then write 0, don't change the state, move one cell to the left and proceed to state Q. Then our optical computer device will have this operation of dividing by 2. Remember, these are 2 parabolic mirrors. And another test gate now labeled with state P. So that when actually the ray enters at a position x coordinate less than 1/2, then according to this test gate, it will leave the test gate to the left. There be divided by 2 means moving the head to the left. And then after that, entering the next test gate with state P to test whether now the x coordinate is greater or smaller than 1/2 again. So that's the next possible rule. And depending on the result of that test, the light ray leaves in this direction or this direction. So that now we have kind of implemented simulation of one rule of the Turing machine, namely this rule, using these 2 devices, and then simulating the next rule. If the finite control says delta of P and read bit 0, then this, or if it reads bit 1, then in this, and we're going to add another blocks here and here. But for now, let's continue our simulation, our creating optical computer with the next rule, namely the rule where the transition function says if you're in state Q and reading 1, what are we going to do then? Reading 1 means that the light ray enters here to the right half of this test box here and leaves to the right. So this case, and let's say that the rule for the Turing machine is in this case, change the bit 1 to a 0, flip it, and move to the right into state P prime. Then our optical computer will have a gate for flipping. Remember, that's our parabolic mirror pair. No, that's our two 45-degree mirrors that we had before. And followed then by a gate corresponding to move to the right. That means multiplying the x-coordinate by 2. And then proceeding to the next branch gate, to the next test. If in state P prime, check whether the x-coordinate is greater than 1/2 or smaller than 1/2, and have the light ray leave in this direction or in this direction. So now we have simulated actually 2 possible transitions of our Turing machine, both starting with a state Q, and depending on whether the bit being read is 0 or depending on the bit being read is 1, we have placed either 2 or 3 additional boxes, each one being a gate. And then we continue that here, placing more boxes in this direction or in this direction, depending on what the Turing machine rules are when in state P, and adding more boxes in this and this direction, depending on what the Turing machine's rules are when in state P prime. And so we continue that for all states, and since it's a finite control, it has finitely many states, so we need to just put together finitely many of such boxes to have calculated and simulated the entire Turing machine. The essential part is, of course, that light rays entering somewhere here might eventually need to re-enter in this direction, right? So there are kind of possible loops, right? Only that the x position of the light ray usually changes when it enters the second time. It will probably enter at a different x position and at a different y position, and then maybe leave here and enter again. And so we can simulate the calculation of the Turing machine step by step. And that's already basically the idea of simulating a Turing machine using an optical computer, using a geometric optical computer. The only remaining obstacle is that all our optical devices are reversible, but the Turing machine computation need not be reversible. So 2 different tape contents, infinite real numbers x and y, could, after one move, result in the same tape contents. So 2 different configurations could result in the same successor configuration, which our optical computer cannot deal with because it's reversible. But fortunately, there's a theorem in computability, which I will prove, for example, in my first promoted course, CS422, Theory of Computation, that every Turing machine can be made reversible. And this approach allows us to simulate any reversible Turing machine using geometric optics. So that's already the end of the construction of how to simulate any Turing machine using geometric optical computing. And this idea, this approach is actually not mine at all. This is taken from a paper that I'm very fond of. It's already like 30 years old, by John Reif, Doug Tigar, and Akitoshi Yoshida, and published in Discrete and Computational Geometry in 1994. And there they have developed these ideas, and I'm just presenting it to you. And as I announced previously, this is the end of chapter 2, and I want to leave you as a cliffhanger with 4 questions to think about as a homework. We want to discuss the answers in our next session, Thursday next week. And the first question is about the efficiency. First question is, how does this geometric optical computer introduced by Ralph and Tüger and Yoshida, how does that differ from photonic computing, as I just showed you in this video? Remember, photonic computing uses silicon photonics and uses optics in order to simulate Boolean operations, transistors, optical transistors. You don't see here any optical transistors. Also, you don't really see many bits. There's only one Boolean test here, right? And another Boolean test. But apart from that, there's this approach has similarities, but also differences to this current hype in photonic computing. And I want you to think about how does this differ from photonic computing. This is to increase your understanding, to raise you up in Bloom's hierarchy of cognitive learning from just knowledge to comprehension. That's the first question I would like you to think about, and we're going to discuss your answers and other possible answers in our next session. The next question I want you to think about is about efficiency. So suppose we are simulating a Turing machine that makes T of n steps, right? Like, for example, a quadratic time Turing machine, n squared steps, cubic time Turing machine, n cubed steps, or an exponential time Turing machine, 2 to the n steps. And if we simulate this in this optical way, how much physical time does it take? Remember, when we talk about Turing machine efficiency, we only count the number of steps, n squared or n cubed or 2 to the n steps. How much physical time does it take here? Does this take seconds or hours or years? How does that correspond? How does that depend on the Turing machine's number of steps to the physical time? This is something I would like you to think about. The efficiency, more precisely, the time efficiency, the velocity, the speed of calculation attained by this kind of optical computer. And the next question, C, is similarly about the memory efficiency. How much physical space does it take to simulate in this way the Turing machine using S of n cells? Imagine a Turing machine using a linear number of n cells, or quadratic number of cells, or cubic number of cells n to the cube, or an exponential number of cells. How much, when simulating such a machine, naturally it takes more and more memory, right? N squared and n cubed. And how does the physical space, the size of this optical computer, depend on that? Do we need larger physical computers, and in what sense? And the last question I'd like you to think about is about whether this is a practical approach, optical computing to simulate digital computers, to simulate Turing machine, or whether it's impractical. And spoiler ahead, there's no right or wrong answer as often. But when is it practical? And when does it become impractical? It's like, remember, for Turing machine is supposed to have infinitely long tape. All computers have only finite memory. So in some cases, a Turing machine is a good way of capturing our digital computers. In other cases, it isn't. And similar, the question is, when is this geometric optical computer practical, and when is it impractical? 4 questions. How does this optical computer differ from photonic computing? How about efficiency with respect to time? How about efficiency with respect to memory, physical space, physical time? And finally, when is this simulation practical and when is it impractical? That's kind of your homework to think about, and we'll discuss that at the beginning of our next session next Thursday. Apart from that, that's already the end of chapter 2 about asymptotic computing. We talked about motivation. We had a recap from very basic from theory of computing about the halting problem and why this is undecidable, what it means to be undecidable, and whether it can be approximated or not. Then we talked about Zeno machines. That means accelerating computation that can asymptotically can make infinitely many steps in finite time. Asymptotically, that's an approximation. We discussed how maybe general relativity allows for realizing such computers. However, it involves a human sacrifice. Namely, your poor professor will need to jump into a black hole for that purpose. And we recalled the experts on black holes, that is Disney movies, on the effects of doing that. Then we discussed theoretically what is the power of such an infinite computation, depending on how often such an infinite computation is allowed to revise its output. Since it keeps computing, it can change its output from yes to no, or from no to yes, once or twice or finitely often. And this is, I quoted you a result from Joseph Schoenfield that characterizes this computational power in the number of oracle queries to the halting oracle, which led us to discuss oracle computation using a mechanical oracle, for example, the Zeno's comb as a mechanical oracle, first finite comb, having lost some of its time, and then an infinitely comb with infinitely many tines, Zeno's comb. And then we discussed how to realize or to simulate a Turing machine, more precisely a reversible Turing machine using geometric optical computation with all its idealization, lack of aberrations, and ask you to think about when and in which sense these idealizations are practical and when they become impractical. And we will continue to discuss Zeno machines in the next chapter. At the end of the next chapter, when we talk about analog computation, this is going to be the content of the next chapter. So now we're going to take a short break, and then I'm going to start with chapter 3 on analog computation, but please keep in mind to think about your homework assignment, which we will discuss at the beginning of the next session. Okay, so now I'm going to pause the recording.